Welcome back. We have started talking about quantum statistical mechanics, and in that context we have introduced density matrices. So, we will talk a little more about density matrices, their properties, and do some example problems, at least one, and then leave a few for the tutorials or the assignments. And then we will talk about indistinguishability of particles and really the exchange statistics that is associated with it. It is a very interesting discussion and should be understood with care and attention, because this really tells you that why in classical mechanics particles are indistinguishable, and in quantum mechanics if you correctly take into account their properties, they should actually be indistinguishable, and that is what quantum mechanics does. So, quantum mechanics is a more correct formalism or a theory, and classical mechanics only comes as a limiting case. Okay. Then we will talk about the classical particles, Maxwell-Boltzmann, obeying Maxwell-Boltzmann statistics, bosons and fermions, from a rudimentary point of view, but we will go deeper into the details and so on as we come to those statistics, that is Bose-Einstein and Fermi-Dirac statistics. And then we will just talk a little about quantum statistics and maybe the canonical partition function, etc. So, let us go ahead with density matrices, and the density matrices, as we have said, is that, so we were talking about density matrices, and the way we have defined it is this rho mn, maybe it is a function of t, because we have written down the equation of motion, and this is k equal to 1 to n a m k. We were not writing it with a bracket, so we will just leave it like that, and then a n k star and a t, and this was a definition of density matrix, which is as you can see that m and n they denote the indices. So, it is like the row and the column, and so it is a matrix. And if we remind you that we have written down similar equation for the phase space density, which was just a value, was not a matrix in classical mechanics. So, the phase space density again written with rho. So, phase space density in classical mechanics or classical statistics was written with this equation. The equation of motion of that is a d rho dt is equal to del rho del t, well this is rho del rho del t plus rho and h, which is called as a Poisson's bracket, and here for the density matrix we write a very similar equation in quantum statistics. As the d rho dt again, which is equal to a d rho dt and plus a commutator bracket of h and rho, and this is really the commutator bracket. So, what was a Poisson's bracket in classical statistics is replaced by a commutator bracket in quantum statistics, and as we said that so rho was just a number. So, rho is a function of q, p and t, whereas here rho is actually a matrix which can be written in terms of these coefficients a m k and a n k, and as it turns out that it takes into account both these averages. One is a quantum mechanical average and the classical the statistical average, that is ensemble average as well. And what we have done is that we have written down that if you have any operator, this is just a recapitulation. So, if you have any operator, you can calculate the expectation value of the operator using the density matrix. So, what you do is that if you you can take a trace of rho and you have to divide it by trace of rho, and if trace of rho is normalized, that is trace of rho equal to 1, then of course the denominator does not come, but this is how the density matrix enters into the discussion. So, this is like the quantum and the ensemble average of any operator. Okay. So, we can also write the density matrix in a slightly different way. Let me also write down this, that what happens to the diagonal elements, and the diagonal elements is nothing but this is equal to 1 over n, and this is a n k square and so on. So, this k equal to 1 to n, and so this is the diagonal element, and let us list out a few properties of this, of the density matrices. Okay. And the properties are that, so one can actually write the density matrix as an outer product of all those psi k's that we have talked about. So, let me write it without an index, so that the summation is understood. So, this is the outer product, and some of the properties are, let us say it is a projector matrix, or it is called as the square of it is equal to the matrix itself, and this is called as a projector property, or it is called as an idempotent matrix. Okay. And second is that the dagger is equal to rho, and from your elementary quantum mechanics, this is called as a hermiticity. So, that rho is a Hermitian matrix. Okay. 3, the trace of rho is equal to 1, and this is called as a normalization, which we have just seen, that this appears that the denominator of the expectation value, and this is equal to 1. And the last one, which is the rho is greater than equal to 0. So, rho is a positive definite matrix. Okay. Okay. So, these are some of the properties. Let us now define, with the aid of this density matrices, which are called as the pure and mixed states. And these are heavily used terminologies in quantum optics and in other fields. So, let us begin with the pure states. So, what are the pure states? If you take an ensemble of objects, or there are members of the ensemble in a given state, say given as some psi, then if the members of the ensemble are all in this state, then it is called as a pure state. So, all members of the ensemble in state psi. Okay. And this is called as a pure state. So, what happens is that in this state, the trace of rho, which is same as trace of rho square, should be equal to 1. And of course, we can define a mixed state where there are ni number of systems, that is members of the ensemble, they are in state psi I. Okay. So, n1 in psi 1, n2 in psi 2. So, that is not a state where all the members of the ensemble, they belong to the same state, same quantum state psi. So, here they belong to different quantum states, like n1 in psi 1 and n2 in psi 2, and so on and so forth. So, what one can do is that one can define a probability Pi, that is equal to say Ni over N, which is the fractional number of ensembles in a state psi I divided by the total number of ensembles, and this is pertaining to the condition that your total Pi is equal to 1 if you sum over all I. So, this rho mix, so this is rho pure, and rho mix would simply be equal to a weighted average. So, this is rho I pure. Okay, so let me write this pure to be here just in case. So, pure, and it's also pure. So, this is that pure states. So, you multiply the density matrices of the pure state and multiply it by the probability, and this gives you the this called as a weighted sum, or it is also called as the convex sum, and so on and so forth. Okay. This has some name. This expectation value of any operator, let us call it as O. So, O is nothing but trace of in such a state, it is a rho, it is not max, it is mix. I mean what I mean is mixed states. So, let me write it as full mixed. So, rho mixed and O. Okay. So, this is the expectation value of the definition in the mixed state. Okay. All right. So, let us try to understand it from this perspective, that if you have these mixed state, they would be incoherent superposition of states. So, we can write down the elements of this mixed density matrix. So, this is equal to mixed. I am writing it sometimes on top and sometimes below, but please do follow a same. So, let us write it mixed here. So, this is P into trace of P into rho mixed. Okay. Oh, sorry, this is rho mixed into O, not P. Okay. So, that is the expectation value of the operator. All right. So, this is that, and then we can write down the matrix elements as in our earlier notation. It is like K equal to again summing over the ensembles, and we have A M K, A N K star, and this is equal to 1 over N, and K equal to 1 to N, and then we have say for example A square and exponential I theta m k minus theta n k. So, what we have written as the A m k is written as A into exponential I theta m k, and there is a phase factor, and this tells you that this is an incoherent superposition of these all these phases. So, all these basis states, and this is finally this can be written as some rho m n in the mixed state is equal to some constant, which is this 1 over n and some A mod square, and then it is really the we can just simply write it as a constant C and write it as the expectation value of these states. And if this it is an incoherent superposition, then theta m k minus theta n k will exist, that there is no definite phase relationship between these members of the ensemble, and that is why it is a mixed state. Okay. So, quickly if you go through what will be the form of the density matrix at different ensembles. So, we can write this as we will start with the microcanonical ensemble, and that is easy to see that the microcanonical, the rho mn should be equal to some rho n delta mn, which means that it is a diagonal matrix. That is, there is no overlap between the ensembles. Okay. So, it has no off diagonal elements. So, it is only the diagonal ones that are there. And what is rho n? Rho n is nothing but 1 by the number of microstates, because when it gets summed over all n, that should give us 1, and then so the entropy can be obtained as k log omega. Okay. And omega is the number of microstates or number of accessible states. Going to the canonical, it is easy to see what it would be in the canonical. In the canonical distribution, one has this thing as again it is diagonal. So, rho mn equal to rho n into delta mn, and it is only that the definition of rho n is given by the Boltzmann factor, which is c into exponential minus beta En, and En denotes the energy states or the modes of the system, where n equal to 0, 1, 2. It may actually skip 0 in some situation, but in general it is there. So, it is exponential minus beta En divided by sum over n exponential beta En. So, this is nothing but equal to exponential minus beta En by z. So, if you are asked a question that calculate the canonical this density matrix in the canonical ensemble. So, it is simply the this exponential minus beta En by z, which we have seen, which is nothing but the probability that our state occupies an energy state En at random among all the available energy states, and it is only allowed to exchange energy with the surrounding or with other members of the ensemble and come to an equilibrium temperature T, which is given by 1 over or which is beta equal to 1 over kT. Okay. So, again you have this rho can be written in terms of the basis states as like phi n and rho and phi n. So, that is the basically nothing but the outer product of this basis states, and you can just simply see that. So, we are not writing it with the operator, but it is an operator, we should know that. So, rho k m is sum over n. I use the completeness of states. So, it is a phi k, phi n, rho n. So, this is actually rho n, and a phi n and a phi m. So, there is a sum over n. So, this gives you delta k n, because this basis is orthonormal. So, this delta k n, rho n and delta n m. Okay. And this is nothing but equal to rho k delta k m. Okay. Now, this is fine. So, this is the canonical distribution density matrix, and we can calculate so if you want to see the matrix form of that, this only tells you what the this term is. If you want to see what the form for the operator is, we can write it down as rho equal to sum over n, and we have a phi n, and we have an exponential minus beta h and divided by z, and there is a phi n there. Okay. And this exponential minus beta h, it actually can be expanded in terms of like say p equal to 0 to infinity, and you have a minus beta h I am writing it a curly H because at times I need to denote also a magnetic field, and this is P divided by P factorial, and this is nothing but equal to exponential minus beta H divided by Z and sum over n and a phi n and this outer product for a proper orthonormal basis, this is equal to 1. So, this gives you that this exponential minus beta H divided by Z, and we have just not a 1, but it is like a identity matrix with all the diagonal entries to be equal to 1 and all the off diagonal entries to be equal to 0. So, we can like this is the form for the density matrix in the canonical ensemble, and if you still want to write down the expectation value of an operator, which is nothing but trace of rho and O. O is written with just a hat just to make sure that it is any arbitrary operator, okay. And this is nothing but equal to 1 by Z trace of O exponential minus beta H, and this is well, there is nothing but trace of O exponential minus beta H and divided by trace of exponential minus beta H. Okay. So, that is the form for this expectation value of the operator in the canonical ensemble, and things are not too different in the grand canonical ensemble, and we simply just write down this . So, your density matrix is 1 over Z G, G stands for grand canonical, and we have exponential minus beta H minus mu n. Now, we need this additional Lagrange's undetermined multiplier. So, H is cannot be considered alone, you have to consider H minus mu n, and that is the matrix that you need to diagonalize in order to get the eigenvalues. So, your Z G is nothing but this is equal to a trace of exponential minus beta H minus mu n, and we know how to calculate this now, and again expectation value of any operators which now need to integrate from, or rather sum over n equal to 0 to infinity. We have introduced this fugacity factor, and then this, and then exponential minus beta H. This mu n is absorbed in the fugacity factor because ZF which is called as a fugacity, we have introduced this before, and this is nothing but equal to exponential beta mu, and this is the expression. And of course, we also have a denominator which is n equal to 0 to infinity. We have ZF whole to the power n exponential minus beta H. H is the Hamiltonian of the system, and that would vary from case to case. Okay. So, this is the important part of this application, or rather this formalism of density matrices. And just to remind you once more that this plays the same role as a phase space density, and it has this additional handle of taking these two averages, such as the statistical average and the quantum mechanical average together. Okay. And here both these averages are taken into account. So, let us do an example and this example is say for example, you take a spin half particles in a magnetic field. Okay. So, magnetic field H. So, that the Hamiltonian of the system is actually minus mu b sigma dot H. Mu b is the Bohr magneton, or the magnetic moment, and you can write it as mu 0 or mu b. It is called as a Bohr magneton. In previous occasions we might have written it with a mu 0. Okay. Now, the question is that obtain the density matrix in a representation one in which sigma z is diagonal, okay, which you are most familiar with. So, we start with the familiar matrix, and this sigma is nothing but the Pauli matrices. So, this is sigma x, sigma y and sigma z, and these are the Pauli matrices. Okay, and because we have talked about spin half particles, presumably we are talking about electrons, but then we do not want to still talk about electrons, because then there are many other things that need to follow, which will definitely come in the recent future. Till then we will just talk about particles, and to make matters more interesting, we also ask the question, what happens when sigma x is diagonal? Now, this is a very important property of this matrices, that these density matrices, that if you change the basis, because we are talking about phi n and phi m kind of basis that it is defined by. Now, we have also defined this properties, that is rho equal to rho square, and the trace of rho equal to 1 and trace of rho square equal to 1, and so on and so forth. Now, what is the guarantee that if you go from one representation to another representation, all these properties get carried over? Is there a proof for that? It should be, because when you calculate the expectation value of an operator, which is a physical observable, then it should not depend upon which representation or what is your basis function or what is the density matrix and so on and so forth. So, this should be independent of that, and you should get the same result. In fact, this is what we are trying to show here, that calculate the density matrix when it is sigma z is diagonal, which is a familiar case, and also calculate it in a situation where sigma x is diagonal, which it is not. Okay. So, we will do this problem to show that first how to calculate density matrix, and second how these density matrices would give rise to same physical quantity, which we calculate as the magnetization here, to show that that is independent of the basis that we choose. So, whether we choose a basis in which sigma z is diagonal, or sigma x is diagonal, or sigma y is diagonal. Okay. So, any of these bases. Sigma y is of course a complex matrix that you cannot change. So, it is 0 1 1 0, just to let you know, because we are not doing a quantum mechanics course here, and we write down this all these Pauli matrices. This is 1 0 0 minus 1. So, in the usual basis sigma z is diagonal, and in the basis sigma z is diagonal, sigma x and sigma y are non-diagonals, rather they have off diagonal the elements, only off diagonal, and this is an important property. If one is diagonal, the other two have to be off diagonal for all the basic relationships, fundamental relationships of the density matrix or of the Pauli matrix to follow, which means that they have to be anti-commuting with some things, and they have to be commuting with some other sort of values, or and their square has to be equal to 1, and so on and so forth. Okay. We do not go into the details of the properties of Pauli matrices, but then you can look at any quantum mechanics book in order to satisfy yourself. In fact, it is good that you should look at these properties of this Pauli matrices, which I simply leave here. So, read properties of the Pauli matrices. So, I hope the basic idea is clear that we are going to calculate the density matrix for each of these cases 1 and 2, and also go one step ahead and show that some physical observable, which is say the expectation value of the sigma z matrix, which is nothing but magnetization, is independent of which representation you take, which basis states you take. So, the solution, and the solution is simple. We have the density matrix equal to exponential minus beta h divided by sum over exponential, or rather trace over this is exponential minus beta h. H is already given in this thing. Let us call it as equation 1. Do not make a try to make a distinction rather between this h on the left side of the equation, which is the Hamiltonian, and this h on the right side, which is written without any curly font. That is the magnetic field. Okay. So, and just without any loss of generality, you take h to be in the z direction. So, the magnetic field to be in the z direction. Okay. So, if you do that, the Hamiltonian simply becomes equal to mu b sigma z h. Okay. So, this is the Hamiltonian that we want to consider here, and this is nothing but because sigma z can take value +1 and -1. So, when you take a trace of that, you have to take a trace over all these two values, which are sigma z equal to +1 and sigma z equal to -1, and we can write down this trace as exponential beta mu b h plus an exponential minus beta mu b h. I hope this is clear. This is the trace, and then of course, we will write down the matrix, which is nothing but again the sigma z is written. This you have to work it out, that really when you take the exponential then of the Pauli matrices, is actually occurs in the like what they would look like in the sigma z representation. So, this is like the exponential minus beta mu b h, and the way you can prove it is simple, is that you have to expand this thing in this form, okay, and then use the properties of the Pauli matrices, which tells you that the even powers of sigma is equal to 1, but the odd powers of sigma is equal to sigma. So, when you expand this, it will have powers of h, which means powers of sigma, and powers of sigma would come as sigma square, sigma to the power 0 sigma square, because you start from p equal to 0. So, sigma 0 sigma square, sigma cube. So, each of this sigma will be there, and sigma square will be equal to 1, and sigma cube is equal to sigma, and so on. So, all the even powers would give you 1, and all the odd powers will give you sigma. Okay. So, this is how you can derive this form that we have just written here. So, okay. So, this is the density matrix for this given problem, and if you now want to calculate the expectation value of sigma z. So, this is equal to nothing but trace of rho, I mean this operator rather, this operator sigma z, which is trace of rho sigma z, and it is easy to see that the trace of rho is equal to 1, and this sigma z, then this is equal to exponential beta mu b h minus exponential minus beta mu b h, and divided by exponential beta mu b h plus exponential minus beta mu b h, and this is nothing but equal to tan hyperbolic beta mu b h, and a result that you have seen earlier. We might have written it with a mu 0. This is that magnetization for this spin half objects, non-interacting spin half objects kept in a magnetic field, and we have shown that this really looks like the tan hyperbolic function, which has a value is equal to plus mu b h, beta mu b h, and minus beta mu b h. So, plus and minus. So, this beta mu b h and minus beta mu b h, and this is the tan hyperbolic of that, the y axis, and this is that. So, this is where the beta mu b h and beta mu b h. All right. So, this is the magnetization which we are aware of. We have seen it from microcanonical ensemble for spin half particles which are placed in a magnetic field, and we have seen it from the canonical distribution as well. But let me now do it from the other representation, and this is a slightly tricky, but you can do it by inspection. So, you have to do it in which the sigma x is diagonal. So, just to remind you that this is where sigma z is diagonal. Okay. So, and here sigma x is diagonal, but sigma x by itself is not diagonal. You have to change the basis for making it diagonal, and because your sigma x has a form like this, which is 0 1 1 0 as written in the lower half of this slide, and you can diagonalize it by a matrix which looks like it is like 1 by root 2 1 minus 1 1 1. This is purely from speculation or rather inspection of that. So, if you do a PT sigma x p, this is like a half, because 1 by root 2 will become equal to half, and then you have a 1 minus 1 we are taking a transpose. So, this becomes 1 and 1, and then you have a 0 1 1 0 1 minus 1 1 1. So, this is your PT, that is transpose, and this is the P which we have taken, and if you multiply this, this becomes exactly same as what we have for the sigma z, which is 1 0 0 minus 1. So, this sigma x becomes diagonal now, and of course, you can again test then what happens to sigma z, and sigma z will become off diagonal, it will take the same form as sigma x. Okay. So, what is the density matrix? The density matrix is equal to rho, this is equal to 1 over 2 and exponential beta mu b h plus exponential minus beta mu b h. This is equal to 1 1 1 minus 1 1, and then exponential beta mu b h 0 0 exponential minus beta mu b h. Let me just make sure that written all those things correctly. Yes. So, this and then a 1 minus 1 at it closer 1 1 and so on, and if you multiply the matrices, you have to know that the matrix multiplication is not commutative. So, you can't do any way that any order of multiplication, you have to follow a certain order, you have to first do it from the right and so on. So, this tells you that density matrix has a form which is equal to half and 1. So, this is the matrix. So, 1 minus tan hyperbolic beta mu b h, tan hyperbolic beta mu b h, and this is equal to 1 again. So, this form is very different than the form that you have gotten here. This cosine hyperbolic there in the denominator, and you have exponential terms in the inside the matrices. Here we have tan hyperbolic terms in the inside the matrices, and we have all the elements including the diagonal and the off diagonal ones. So, the density matrix can be different in different representations, because it depends on the basis that you choose, but that will not deter the expectation values of operators, which are physical observables, to change values, because they should be independent of the basis chosen. And similarly, if we start doing sigma z, remember we should still calculate the expectation value of sigma z, because that is what the magnetization is defined. So, the magnetization is the expectation value of the z component of the spin angular momentum, which in this case is sigma z. So, this is equal to like a trace of half 1 minus tan hyperbolic beta mu b h and a minus tan hyperbolic beta mu b h and 1, and this is a 0 1 0 minus 1 minus 1 0 and so on. That is the form of sigma z in a representation. It is not exactly sigma x, it is minus of sigma x in the representation in which sigma x is diagonal. We have not shown this, but you convince yourself that this is true yourself, that this is sigma z in a basis where sigma x is diagonal, and if you calculate it, it still comes as tan hyperbolic beta mu b h. Okay. And so, this is the result that we got earlier in some different contexts, solving this using microcanonical and canonical ensemble, and then we get the same result here as well. Okay. So, that tells you that these really in calculating the quantum statistical average of operators, this density matrix is quite helpful, and finding out density matrix is not difficult. It only sort of demands or requires that you know the Hamiltonian of the system. Okay. And that is how you calculate this. We have of course done it for a very simple case where there are spin half particles. So, it is just like a 2 by 2 matrix. In more complicated situation, it could be a larger dimensional matrix, could be an infinite dimensional matrix as well. Okay. All right. So, now I will discuss something very important, which is called as the indistinguishability of particles or identical particles. This is very important, and one needs to understand it well. So, identical particles and indistinguishability. Okay. All right. So, this is a very important thing, as I said. So, what I want to tell you right at the outset a priori is that the definition of identical particles is really same in classical and quantum physics, but they have differing implications. Okay. It is quite a sort of powerful and tricky statement. Let me try to explain that what kind of different implications could it have for identical particles. And it is not difficult to imagine that if you have a system of electrons or a system of photons or a system of phonons or any other quantum object, quantum particles, leptons and so on, baryons, they are intrinsically indistinguishable. You cannot say one from the other. Okay. So, if they are, then what classical mechanics did so far in terms of distinguishability, and one particle description is fine, because you know that you are just talking about one particle and nothing else in the universe. But when you have many particles, at least two particles, how would you distinguish one from another? And as I just said that the definition has to be same in both classical and quantum physics, but they vary or they differ by their implications. Let us see how it does. Let me draw a billiard board. Okay. And this billiard board has say these balls, let us say that these are 2 balls, and even if I know very well that they are identical, because we are talking about identical particles, say they are identical, I still have to write for our discussion to proceed as B1 and B2. So, ball 1 and ball 2 are the 2 sort of balls at the 2 corners of a billiard board, and let us see that this is at a time t equal to 0. Okay. Now, what will happen is that the billiard ball would be hit and will reach somewhere on the other extremity at after a time t, and let me show these things by 2 different colors. So, let me show it by this blue color, that this actually goes like B1 goes to this end and B2 goes to this end, and they are now at t equal to t, we are these 2 balls that are went to this part. So, but there is also another possibility that you see that they can actually go like this and they can go like this. Okay. So, say for example, an observer P1, he claims that the blue line is correct. Okay. And he takes the initial data. So, his initial data was that the B1 and B2 are at these corners, the lower corners at t equal to 0, and then he takes a data at after time t. He predicts that B1, let me write it as these edges as 1, 2, 3 and 4. Okay. So, he predicts that after time t, B1 goes to, say for example, so he says that let us B1 goes to 4. So, that is along the red trajectory, and B2 goes to 3. So, this is the red trajectory. Another observer P2, he also takes data, and after some player has come and hit the ball so he predicts that this goes to 3 and B2 goes to 4, okay. And this is the blue trajectory, a blue path. Of course, both can be correct, we know that, because forcefully we have named them, but they are identical. So, they cannot have any name associated with them. So, an independent observer actually would find that both are correct. So, a third independent observer claims both to be correct, and he is unable to resolve this conflict that what P1 claims or what P2 claims, which one is correct, and he is actually very correct by saying that, because these are indistinguishable particles and both seem to be correct. So, what allows us to distinguish one situation from another, that is the situation in which P1 reports and the situation which P2 reports. Okay. the distinction lies, of course, on trajectories, that is whether it is a blue trajectory or a red trajectory, okay, which means that it depends on history, that is which path, you can either call it history or trajectory, they mean the same thing, in the sense that how they went from one identical particle went from from this corner of this thing, from this 1-2 position to the 3-4 position and so on. So, this history is known in classical mechanics, but not in quantum mechanics. There is no definition of the path follows in quantum mechanics. No such history is known. Quantum mechanics. Okay. This is a very important statement and a very powerful statement as well, that we are unable to know which path do they follow. And if you have any question that how does classical mechanics know, do we really solve Newton's laws and know this exact path? Probably in a simulation, if you do it, if you sort of discretize this, the forces, if you know the forces acting and then numerically solve, you probably can generate the path, but any other path is also possible, and that answer is very nicely given by the by your Lagrange's formalism. Okay. So, we know that the path that it follows, actually for in that along that path the action has to be minimum, or the LDT has to be has to be minimum or extremum along that path. So, even if the Newton's laws do not really specify this, there are many ways of going from one to another, that is initial xi ti to xf tf, I and f they stand for initial and final, but the Lagrange's equation of motion that inherently and implicitly assumes that these equations of motion which are identical to that the Newton's laws, they actually take into account the correct path that is followed, and the path that actually the particle takes is where the Lagrangian density, this L is the Lagrangian density, and then dt, and so integral of that is minimized, which means delta of that is equal to 0, and this is called as an action. So, delta of x equal to 0. Okay. We will not go into details of that, but then there is nothing like this in quantum physics. Quantum physics does not really care, or it is possible to construct a path through which the particle goes. We only know about the probability density for a particle to be found at a space time point, nothing more than that. There is no trajectory that could be generated in quantum physics, and this is the inherent difference between classical and quantum physics, where the distinguishability and the indistinguishability become so important, and the statistics become important. And as you have seen that the Gibbs paradox tries to take into account in a sort of hand waving manner by dividing either the canonical partition function or the entropy by some factor of n or n factorial, and then do some get some results for the Gibbs paradox, that is if you allow two identical gases to mix, there should be no change in entropy before mixing and after mixing. So, the entropy of mixing is equal to 0, and no such things are required for quantum mechanics, and that's the power of quantum mechanics. Okay. So, let's just look at a little about the symmetric and antisymmetric wave function, that these under the exchange that happens to the wave function. So, if you have a particle A and a particle B, and if you take A to B and B to A, then classical mechanics demands that it is actually a new state, a distinct state that needs to be taken into account, or there is a distinct configuration that has to be incorporated. Quantum mechanics says no, they are the same state. They can at the most vary by sign, that is a phase factor. And let us just try to sort of put it with some symbols and so on. So, we have say a wave function consisting of two particles, and we simply able to write it, we are able to write it with just a ket, say A and B, and the particles, if they are by interchanging them, this becomes B A, and it becomes a distinct state as far as classical mechanics. So, these are classical mechanics, even though you do not see a wave function, but we are simply talking about a say in the PQ space or in the phase space, this is just a configuration that we are talking about. So, this classical mechanics would yield that psi and psi prime are distinct. Okay. But in quantum mechanics, this is not distinct. In fact, this is equal to psi equal to A B equal to some alpha psi prime, and this is equal to some B A. And you know that in quantum mechanics, if you multiply a state or a ket by a number or by a factor, constant factor, then the state does not change, because for getting a new state, that state has to be orthogonal with respect to the earlier state, and they have to be linearly independent, and clearly this is not linearly independent. It is just there is a phase factor that multiplies this one state to another. So, these are not psi and psi prime are not distinct states and related to each other. Okay, so that seems fine. So, from here on we have written it as alpha, which means that alpha is some number that we have not committed ourselves, and here we go and can define there are two kinds of combinations. One is called as a symmetric combination of states, which tells you that this psi has to be like 1 by root 2 and A B and a plus B A. Why is this symmetric? Because if you change A to B, it does not pick up a sign, it just the second term becomes first term and the first term becomes second term, it just does not matter which one you write first inside the bracket. So, this is like a symmetric combination, and an antisymmetric combination is also there. And it tells you that this, so let us write it as symmetric here and antisymmetric here, and it is just comes with a negative sign. Okay. Now, you see that it is antisymmetric because if you change A and B, there is a sign, there is a mutual sign, negative sign that comes in. Okay. Okay. Let us try to make it a little more physical or something that instead of A and B. Let us give an example that we are talking about particles inside a one dimensional potential box, which means there are infinite walls there and the particle is really trapped within that. And let us think that the two particles are trapped in n equal to 3 state and n equal to 4 states. So, two particles trapped in 1D potential box, okay, from 0 to L. Okay, so, and we want to write down the symmetric and the antisymmetric combination, and let us write down the symmetric combination easily, which we know is 1 by root 2, and we still continue that notation in terms of this. So, instead of A and B, we now write it in terms of these n1 and n2 and so on, but they mean the same thing because we use the basis that is most convenient to us. And if you remember, the basis for a particle in a box is that this En is really quantified by this n square pi square h cross square by 2 m l square, and the psi n is, if it is a 0 to L box, then it is root over 2 by L sine n pi x by L. Okay. So, of course, if it is a symmetric box, that is between minus L by 2 to plus L by 2, there are there are parity symmetric solutions would come where n will only be equal to even for this solution, and for n odd you will have to have a cosine solution. So, this is fine. So, we will write this as in the n1 n2 basis. So, we will write it as 3 4 and a 4 3. Each one of them is like, so each n n1 n2, it is like your root over 2 by L square, and it is a direct product of these things. So, it is like sine 3 pi x over L, sine 4 pi x over L, and so on and so forth. Okay, so, that is the product state, and we have taken a square of that and so on. So, this is the meaning. So, there is a symmetric combination, and if you want the antisymmetric combination, we have written this S to be outside. So, let me have this S to be inside for the symmetric and A for inside the ket notation. So, psi A is equal to again 1 by root 2. You can write it in this notation, or you can write it in this notation as well. That is, you have a psi 3. Okay, let me write just 1, then that will be clearer. So, any n state is like root over 2, and it is a n pi x by L. Okay, that is the thing. Let us not write a product state, because this is what we want to show, that psi 3 x 1 psi 4 x 2 minus of psi 4 x 1 into psi 3 x 2 and so on. So, this is the antisymmetric combination. So, we can write this as well as the symmetric combination. It is a psi 3 x 1 psi 4 x 2 plus psi 4 x 1. Well, let me just squeeze it in here, psi 4 x 1 multiplied by psi 3 x 2. Okay. So, this is the symmetric and the antisymmetric, and very nicely this antisymmetric part can be written as a matrix, or as a determinant rather. This is called as the Slater determinant, and the psi 4 x 1 and the psi 3 x 2, and there is a psi 4 x 2 and so on. Okay. So, this is called as the Slater determinant. So, the antisymmetric wave function can be written as a determinant. So, if you take the determinant of that, you will get the step that is you see above. Okay. All right. So, for a larger number of particles, it is a little complicated, but nevertheless it is still doable. Say for 3 particles, it is instructive for you to learn. So, for symmetric, we can write it easily because it is a 1 by 3 factorial, and we will just use this the Fogg basis, as it is called, the number basis. So, it is or rather we just simply use this the same context that we have done. So, it is n1 n2 n3 plus n1 n3 n2 plus n2 n3 n1, all the permutations that are possible, n2, n1, n3, and so n3, n2, n1, and n3, n3, n1, n2, and so on. Okay. So, these are all the permutation of the pairwise particles. Like this one is just the same order, and then we have kept n1, the first particle, to be in n1, and then n3 and n2 are swapped, and so on and so forth. So, one is able to make the 6 combination, and the normalization demands that there is a 1 by n factorial, and this one for the antisymmetric, you just need to understand that for these pairwise exchanges, for one pairwise exchange you should pick up a negative sign, just like this negative sign that you have it here, that let me show it with the color. So, this is the negative sign that we are talking about. This is here. So, the pairwise exchanges will have a negative sign, but 2 pairs of such exchanges will bring back another negative sign, which means that it should come with a positive sign. And so, this positive and negative, all these things can be written a little carefully, and if you write them down, it is like n1, n2, n3 minus n1, n3, n2, because that there is one exchange, and then there is the 2 exchanges, which is n2, n3, n1. So, it is a negative sign, and then it is a n2, n1, n3 that has odd exchanges, and plus again even exchanges n3, n1, n2 minus n3, n1, n2, and so on. Okay. N3, n2, n1. Okay. So, this will give rise to a sort of this Slater determinant, which gives you say for example x1, n2, x2, and n3, x3, and so on, n1, x2, this is sorry, this is n, so this x1, x1, x2, psi n2, x2, and psi n3, x2. Okay, and this is psi n1 x3, psi n2 x3, and psi n3 x3. Okay. Now, it is written correctly, and it is the Slater determinant. So, we should simply draw a vertical line there. So, this for 3 particles, you can exchange it to larger number of particles. Again, this 2 particle, let me take a mod square of that. So, we want to calculate the probability for the symmetric and antisymmetric cases. Okay. So, S and A both, if you write it for these 2 particles, which are could be at the locations this. So, we have a S. So, again go back to the 2 particle, because 3 particle is too complicated to write this modulus, because you have to take many terms. So, S A x1 and x2 mod square, and this is nothing but equal to half of this, and then you have a mod square of psi 3 x1. We go back to our original problem of n3 and n4. So, that, and then we have this psi 4 x1, psi 3 x2, and so on, this and the mod square. Now, the plus sign is for the symmetric, and negative sign is for the antisymmetric. And if you open the bracket, this is really psi 3 x1 square, psi 4 x2 square, and a plus a psi 3 x2 square, and psi 4 x1 square, and plus minus you have a psi 3 star x1, psi 4 x 2, psi 4 star x 2 and psi 3 x 1. That is one interference kind of term or mixed term, and then you have a psi 4 star x 1, psi 3 x 2, psi 3 star x 1 and a psi 4 x 2. Okay. So, this is the probability density for this each of these states, and this is very interesting. The interesting thing is that the first two are predicted by this third observer who came and joined the game at that capital T time. So, he could only see this, but however, a quantum mechanical system, in addition to the two terms, they need a crucial interference term. And in fact, if you remember Young's double slit experiment, this two terms, the first two terms is not important, or rather they are important, but they are not crucial in explaining the interference pattern. The interference purely came from the last two terms. So, the classical observer who joined at small t equal to capital T, that is at a later time, he sees that this P, that is the P1 observer and P2 observer, or the vice versa, and he sort of said that both are correct, and he was correct, but then he missed all these main ingredients of the quantum theory. Okay, so let me now sort of quickly do this different ensembles and or rather this different distribution, and let us take a simple case in which we have two particles and three states and so on. Okay. So, basically introduction to quantum statistics. So, the first one is Maxwell-Boltzmann statistics. And what it demands is that it sort of you take any particle in any state, and there is an overall factor of 1 over n factorial that should come in counting the number of microstates that are possible. So, your omega would simply become equal to 1 by n factorial and then sum over k, and then you just sum over these one microstates which is between an energy E and E plus d, or it is sort of restricted in energy space or in the number of particle space, and so on and so forth. So, this is how the Maxwell-Boltzmann statistics is reconciled, that since we are talking about it in the same bracket as the other two statistics, let us just talk about that there are, let us not talk about distinguishable and indistinguishable particles for the Maxwell-Boltzmann statistics, which of course we know that it is valid for distinguishable particles, but if you are talking about it in the same bracket as Fermi, Dirac and Bose-Einstein, let us just say that you treat them as distinguishable, yet you divide it by this n factorial number in counting the number of microstates, just like what we have shown here, and there is a crucial n factorial term required, which is called as a Gibbs correction. Okay. And it is only true in the limiting sense of the other two statistics, which we are more interested in. So, we will write down this the Bose-Einstein as, we will tell you about the some as historical thing about Bose-Einstein statistics and so on. So, this Bose-Einstein statistics, it tells you that any number of particles can occupy a given quantum state, okay, or given energy state, and there is no need for this n factorial. So, this is an important thing, there is no correction that is needed. Okay. And of course, here in the Maxwell-Boltzmann we can simply go ahead and calculate the partition function, which would give rise to this exponential minus beta e k, and we have seen this how this gives rise to, or rather avoids giving the wrong results by the mixing of these gases, two identical gases, and this is called as the Sackur-Tetrode equation, which we have seen. Now, this Bose-Einstein, any number of particles can occupy any energy level, there is no need to have this thing. And similarly, in the Fermi-Dirac case as well, we do not have any statistics. Again, no n factorial needed. Here, any number of particles can occupy any state. Here only no two particles can occupy a given state. Okay. So, bosons are they love the presence of other bosons, whereas these are completely, they repel any other fermions that come into their vicinity and so on. And this gives you the main difference between the three statistics, and we will see examples of that. We would in a simple situation we will start with some few particles in which can be distributed in few energy states, and do these calculate this distribution and calculate the partition function, maybe the canonical partition function for those, and show that what are the differences between these three statistics in very simple situations. And then we shall go ahead and talk about many particles and introduce these statistics in from a more formal perspective, and finally we would go ahead and do exercise on each of those or rather applications of each of those statistics in various physical situations. For example, the Bose-Einstein statistics would give us the right specific heat expression for phonons, say for example, or it would give rise to the radiation pressure due to a black body, or due to electromagnetic radiation, the pressure due to that. Or you have these fermions will talk about metals which are free electrons, and we can talk about the Pauli paramagnetism, or we can talk about these white dwarf stars which are taken as, or which can be considered as a very extremely degenerate Fermi gas. And we will do this calculations or rather these example problems or these applications on these various statistics. So, I hope the idea has been made clear in this week that we are really getting into quantum statistics. There are various corrections or fixations that need to be done for one to actually transit from the classical statistics to quantum statistics. So, we will carry on with quantum statistics from next week onwards. Thank you.